Langford in Basic Photography explains this idea with the diagram of which this is a variation of. The first thing you have to remember is that when a lens is focused on a plane, it is only focused on that plane. Either side may or may not look in acceptable focus, but actually the lens is only focused on that plane. When the lens is focused in this plane, at this point a point of light looks a point. However, as you go out in either direction, the point of light begins to resemble a small circle or even a larger disc. These are called circles of confusion, and if the circles of confusion are sufficiently small, then the image looks in focus. When the circles of confusion begin to look like circles, then we can recognize that image as being out of focus. For the purposes of my exercise, my circles of confusion are these 5p pieces. These two lines represent my lens and indeed the aperture of my lens. This point represents the point at which the lens is focused at. This is a little bit like the Father Ted episode where Father Ted has to tell Father Dougal that there's a difference between small and far away. When we hold the camera to our eyes, the camera is everything. The camera is huge. Everything else then is small in relation to the frame. That's really important. So, using my trusty Royal Mail size guide, I can see that I can draw a straight line from the top of my aperture and the bottom of my aperture here. So this represents the point of focus, and these are my circles of confusion getting bigger in this direction and bigger in this direction. If I put my 5p's in till they touch the lines, I could argue then that my depth of field extends from here to, say, here, and we'll call that F2. I decide to shut my lens down, so I make the aperture smaller. Let's close it down to, for argument's sake, F8. Here then I draw my lines again, this time in blue. Put my circles of confusion back onto the diagram, and now this one touches here and it touches here. So if I draw from here to here, that would give my depth of field at F8. That seems fairly straightforward, and that's the way that it's portrayed in a lot of textbooks. I've redrawn the diagram to show the imagined closest focusing point of the lens, and as you can see that the depth of field here is quite narrow. What I like about this diagram is that you can demonstrate how depth of field changes with distance. So if I instead focus at this point here, back in my circles of confusion. You can see from this diagram, although I haven't changed my aperture, my depth of field has increased simply by focusing on something further away. And that's really how it works. However, this isn't how it works. This really isn't how it works. This is a massively oversimplified diagram of the way it works. And with the next diagram I will try and attempt to show you a different version which will explain something fundamental about depth of field which this doesn't. Here's a slightly different way of looking at it. Imagine these inner lines are my original lens from the previous example. My circles of confusion extend from here to here. Now imagine this is on a 35mm or full frame DSLR. A normal lens, which gives me an angle of view of around about 45 degrees, is 50mm. If for argument's sake the internal diameter of the lens was 25mm, that would give me f2. If I scale it up to a medium format camera such as the Hasselblad, the standard lens is now 80mm lens. I still want to get f2, so 80 divided by 2 gives me 40. So if this represents a 25mm gap, this would represent a 40mm gap. Okay. Because the film size, or if you prefer sensor size, is physically bigger, then my circles of confusion move in. At the same f-stop, in this case f2, my depth of field is less. This would explain why the smaller the sensor you have on a digital camera, the more depth of field you have for a given aperture. So on my Olympus, which I'm filming this with, which is a micro four thirds sensor, the sensor is a lot smaller than my D600, which is full frame. Therefore, at any given aperture, I have more depth of field. So here's a different way of looking at it. In the previous example, I assumed that we were focusing on a point, when in fact we're never focusing on a point, we're actually focusing on a thing. So this will be my highly accurate description of a tree. So let's draw my lines in again. A beam of light from the top of the lens will cross there. A beam of light from the bottom of the lens will cross there. However, if I draw this line in from the top of the lens to the bottom of the tree, then the bottom of the tree, the bottom of the lens to the top of the tree, then I get this area which is in focus. And you'll notice that this area, which I could call X, is half the size of this area, which I can call 2x. Therefore, my depth of field extends 1/3 in front of the object and 2/3 behind the object. Let's put those out. So, if then I choose to stop my lens down, to say there, I can do the same thing. I go hang on, not that far. So now my depth of field goes from here to here. And the smaller I make the aperture, the more my depth of field extends. That kind of makes sense, except that actually it's no more realistic than the first example. If I give my tree double the height, on this basis, I end up throwing the lines out and ending up with a new set of light rays and a new depth of field, which obviously makes no sense. But if you combine the two diagrams, this one, which gives the idea of the depth of field extending 1/3 to 2/3, and the previous one, which explains the role of circles of confusion, then you do get an appreciation of what is actually happening inside the camera. The third way of looking at this is to resort to the maths. To calculate our depth of field, we actually have a deceptively simple equation. It is HU over H plus U for the farthest point, and HU over H minus U for the nearest points of the depth of field. So here is my lens, and here's my focal plane. So this would be HU over H minus U, and this would be HU over H plus U. Okay, well the U is the focusing distance, so from here to here, that will be U. The H part, well, that's a bit more complicated, and here's where it kind of goes wrong for me. So H stands for the hyperfocal distance, and that is defined as the focal length of the lens in millimeters squared over the f-stop times the circle of confusion. Now clearly I know this, but I don't know what this is. Having run a few figures through it, what I can say is that if you lower this number, which is the focal length of the lens, you get more depth of field than if this number is high for a given f-stop. So I conclude then that the longer the focal length, the smaller the depth of field for any f-stop, and that's really quite useful to me. Wide angle lenses give me more depth of field than telephoto lenses.